Alright, let's talk about valence shell electron pair repulsion theory, or VSEPR, as it is called for short, or VSEPR, depending on who you talk to. I usually call it VSEPR. What this theory is all about is the shape of molecules. This theory tries to predict the shape of molecules and polyatomic ions using the fact that electrons really don't like to be near each other because they are they have the same charge. They're like in sign in terms of their charge. They're negatively charged groups. Groups of electrons are repulsed by each other. They push each other away. This repulsion of one group of electrons by other groups of electrons means that we can predict the shape because there are certain geometrical shapes that will result in those groups being as far away from each other as possible. You can have a practically infinite number of ways that you could theoretically arrange electrons, but there is always one optimal way to arrange them so that everything is as far away from each other as they possibly can be. And that is what VSEPR does, is it says what is the best geometric shape to get these groups as far away from each other as possible. And it is a little bit more complicated than that, but that is really the heart of the matter, is just how far away can we get these things from each other. So when we have a molecule like this one, for example, that has two groups of electrons on the central atom, and it's really, there's kind of a couple key things in that statement there. Groups of electrons means not just how many bonds do you have, but how many groups of electrons that do you have. So this double bond here and this double bond here, even though there are two individual bonds in the group, they are together. Both of these bonds are in the same region. They are working towards the same goal, if you want to think of it that way. They are considered one group. Kind of similar to how a lone pair, while it is two electrons, it is still considered as one group. But when it comes to VSEPR, we're concerned with groups of electrons, and we are concerned with the groups that are on the central atom. The central atom is really what we care about. We don't care quite so much about the terminal atoms. So even though this is technically a group here, when we're trying to figure out what shape is this molecule going to have, we don't care how many lone pairs are on the terminal atoms. We only care how many bonding groups and how many electron or lone pair groups are on the central atom. That central atom is the key. So in this particular kind of molecule here, where you have two groups on the central atom, the geometry for this is always going to be what we call a linear geometry. And what that means is the two groups that are attached to the central atom are on exact opposite sides of the central atom. They are 180 degrees apart. They are as far away from each other as they can get, and that is 180 degrees away. And this will always be the case if our central atom has two groups attached to it. If it has two groups, the farthest away they can get is 180 degrees. If we have three groups, it gets a little bit more complicated, mainly because now we're starting to get into molecules where we can have lone pairs on that central atom. Technically speaking, you could have an atom or a molecule with a single bond and a single lone pair, so you just have two things on the central atom. But in that case, there's not really a central atom because there's only two atoms. But when you have three groups, this is when you really have to take into consideration the possibility of having a lone pair on that central atom. And when we do, the geometry that we get as a result is that we're going to have our central atom, and the farthest away we can get these three different groups, so again, the two double bonds here are each just one group, We don't care how many bonds there are, we care how many groups there are. And single, double, and even triple bonds only count as one group. So we have two bonding groups and a lone pair group. So with those three groups, the farthest away they can get is being in a plane together. So they're all in the plane of the screen, if you will. They're in a plane together, and they're 120 degrees apart. So there's 120 degrees here. This is also 120, and this is 120. In reality, it's not exactly 120, but for our purposes in this class, we're just going to go ahead and call it 120. In reality, this is actually a little bit less than 120, and these two are a little bit more than 120, but it's not drastically different. It's not like these two are 110 and this is 90 or anything like that, or whatever it would be. It'd be 100, I guess. It's not that drastic. They are scrunched a little bit. That lone pair is a little bit big, and so it pushes. But for our purposes, we're just going to call each of these 120 degrees. They're all in a plane together, and there's 120 degrees between all of them. We call this particular molecular geometry bent. And the reason for that is because when we're naming a molecular geometry, all we care about are the bonds. We actually ignore the lone pair when we are naming things with naming things according to their molecular geometry. So when we're ignoring the lone pair, then that just kind of goes away. What this looks like, if we're ignoring that lone pair, it looks like somebody took a linear molecule and just kind of bent it. They took that linear molecule and bent it down to 120 degrees instead of 180. And so this, because of that, is called bent. Now there is a second name that we can give this. So that is the molecular geometry name, but the electron geometry is called trigonal planar. And electron geometries care about all of the electron groups, not just the bonding groups. And so this is called trigonal planar because you have three things attached to the central atom. Trigonal, three. So you have three things attached to the central atom, and they're all in a plane together. So trigonal planar is the name of the electron geometry for this. And if you have a molecule where all three of the things attached to the central atom are bonding groups, like this one, for example, because we have a bonding group here, bonding group here, bonding group here. Actually, let me make a circle because it looks like I just made that a triple bond. So that is not a triple bond, that is not a double bond, so we just have three bonding groups here. This, the molecular geometry, is actually also called trigonal planar. So because now all the groups on the central atom are bonds, and because, again, molecular geometries only take the bonding groups into consideration, this geometry is the same as the electron geometry was up here, and so we just give it the same name. It is trigonal planar. So this is trigonal planar for both the molecular geometry and for the electron geometry. They are both trigonal planar. We can take this one step further here and talk about molecules that have four groups attached to the central atom. If all four of those groups are bonding groups, we're going to call this type of structure tetrahedral. And this is actually the first structure that we're seeing here that gets into the third dimension. The previous three that we've seen here, the bent structure, trigonal planar structure, and linear structure, everything in the molecule was in a plane together in the structure. So you could, if you remember your geometry, you could have a plane, and you could put every molecule in the structure in that plane, in that two-dimensional plane. That is not the case with when you get to 4 groups. When you get to 4 groups, you do actually have to go into the 3rd dimension, and with tetrahedral structures, you have 4 groups attached to the central atom, and they are going to be 109.5 degrees away from each other, essentially in every direction here. So this atom is 109.5 degrees away from all 3 of these other atoms, not just this one. It's 109.5 away from all of the other terminal atoms. And the same thing can be said for this atom. It's 109.5 degrees away from this one, and that one, and that one. So they're all the same. They are, I guess you can call them degenerate positions, or they're energetically equivalent positions here. So this structure is tetrahedral. If you remember back the Greek prefixes we used for naming stuff, tetra meaning 4. So tetrahedral, it's like a 4-sided shape here, is what you end up with, where you have 109.5 degrees for everything. And that is as far away from each other as they can get. There is no geometry where you can get all of those farther away from each other than 109.5 degrees. If we change to a molecule that still has 4 groups, so we still have 1, 2, 3, 4 groups on that central atom, but now one of those groups is a lone pair instead of being a bonding group. So we have a lone pair in the mix here. Now the electron geometry does not change. So the electron geometry in this situation is still tetrahedral. And that will never change. If you have 4 groups on the central atom, the electron geometry is always tetrahedral. What will change is the molecular geometry. Because again, the molecular geometry only takes into account the bonds. So the molecular geometry is now going to be called trigonal pyramidal. And I'm not going to write that name out, it's just right here. So trigonal pyramidal is the name of this molecular geometry, and it gets that name because if we ignore the lone pair and just look at where the bonds are, this type of molecule is always going to look like a 3-sided pyramid. So it's like we have 3 points on the base here, and they all lead up to the tip of the pyramid here, so it is a 3-sided pyramid structure. So trigonal pyramidal is the name of that. And so any molecule, not just ammonia, any molecule where you have 4 total groups and one of those groups is a lone pair will have trigonal pyramidal molecular geometry. If we have the same kind of molecule in that we have 4 groups on the central atom, so water is an example of this, where we have 1, 2, 3, 4 groups on that central atom, but now 2 of those groups are lone pairs, so we have 2 bonding groups, 2 lone pair groups. Regardless of whether these groups are single or double bonds, for our purpose they could only be single bonds because we haven't talked about expanded octets. In reality, you actually can have molecules where an atom inside of them can have more than just 8 electrons. For our purposes, though, we're only going to look up to octets. So these are only ever going to be single bonds. But for these types of molecules where we have 2 lone pairs and 2 bonds, the molecular structure is going to be called bent. Just like back here, where we had 3 groups and one of them was a lone pair. And the reason for that is if you look at the shape, this shape, if we're only looking at the bonds, is remarkably similar to that. They are almost identical. The only difference is about maybe 10 degrees in the angle here, because again, this is still roughly 109.5 degrees, and the other one was about 120. So, because the only difference in the shape is a little bit of difference in that angle, we just go ahead and give it the same name. So this is called bent. But again, the electron geometry here is still tetrahedral, because we still have 4 groups of electrons, and they're all 109, roughly 109.5 degrees away from each other. So the electron geometry, where the electrons are positioned, is still just tetrahedral in shape. We have this 4-sided pyramid. But if we're only considering the bonds, it's not a 4-sided pyramid, it's more like a pipe that someone kind of bent in the middle. And so we give it a bent. We give it the name bent. So these are all summarized here on this nice little table for us. And as you can see here, it tells us, if you have 2 electron groups and both of them are bonding groups, that means that your angle is 180 degrees, and that is called a linear molecular geometry and electron geometry. If you have 4 electron groups, one of them is a lone pair, and 3 of them are bonding groups, that would mean that your electron geometry is tetrahedral, your bond angles are 109.5, and the molecular geometry is trigonal pyramidal. So this is a really handy tool for you to use as you're working through VSEPR. All you have to do is figure out how many bonding groups do I have, how many lone pairs do I have in my molecule, and the table will tell you the names and the angles for everything else in the molecule. Alright, let's do a couple examples of these real quick here. So go ahead and pause the video. Actually, before you pause the video, just to tell you how you're going to solve these problems. Most of the time with VSEPR, if you're trying to work out the VSEPR structure yourself, what that means is really you're going to write the Lewis structure and then use the Lewis structure to figure out how many bonding groups do I have, how many electron lone pairs do I have on the central atom. So with that in mind, that you'll need to draw the Lewis structure, go ahead and pause the video and try to predict the geometries, both electron and molecular, for PCl3 and nitrate. Alright, so hopefully you worked out both of those to the best of your ability. Let's talk about each of them now. Like I said before I had you pause, we need to work out the Lewis structure for each of these things first. And now one of these we actually already did. I didn't think about that before I told you to pause, but we actually already worked out the Lewis structure for nitrate. So if you remember, and I'll just make this one the double bond this time. Why not? This was the Lewis structure for nitrate from the previous slides. PCl3 we did not work out, but this is our skeletal structure. Make it as symmetrical as possible. Phosphorus has 5 valence electrons. It has a lot more than 5 total electrons, but remember we're only doing valence electrons. So phosphorus has 5, chlorine has 7, and we have 3 chlorines. So this means we have 21 plus 5, which is 26 electrons to put into our structure. We already have 6 in the bonds here, so if we just pick a chlorine and start putting them in, 8, 10, 12, 14, 16, 18, 20, 22, 24. Last 2 are going to go on that phosphorus. If we check, everything that wants an octet has one. And so we are good to go to work out the VSEPR structures here. So again, all we have to do for each of these is just work out on our central atom, because again, all we care about is that central atom. We do not care that there are lone pairs all over the place on these chlorines. There's everywhere. We don't care. We only care about that central atom. So how many bonding groups do we have? And how many lone pairs do we have? For this particular molecule, we have 3 bonding groups, 1 lone pair. So if we go back to our table and check, if we have 3 bonding groups and 1 lone pair, then our electron geometry is tetrahedral, and our molecular geometry is trigonal pyramidal. And I guess well, I'll go ahead and write those in. Tetrahedral is our electron geometry, and trigonal pyramidal. I did not mean to do that. Oops. Let's get back in there. Pyramidal. There we go. That is our molecular geometry. So for nitrate, we're going to do the same type of thing. We're going to check just the central atom. How many electron groups does the central atom have? If you thought 4, then what you were doing was just counting the bonds. We don't want to count the bonds, we want to count the groups. And the nitrogen has 3 groups around it, because again, that double bond counts as 1 group. So we have 3 bonding groups and no lone pairs on our central atom. And if we check that, 3 bonding groups and 0 lone pairs is trigonal planar for both geometries. So that is electron and molecular geometries. All right. In the next video, we are going to talk about electronegativity and polarity. And I might talk a little bit about drawing molecules like this, but I'm not going to spend too much time on that. The main topic will be electronegativity and polarity, and talking about how we can tell if a molecule is polar or not. So I will see you in the next video.